All right, we're going to move on with our acid-base notes. We're going to be moving on to pH and pOH scales and the calculations that involve that. So the pH scale indicates the hydrogen ion concentration. That can be written as H3O plus or sometimes you'll just see it shorthand as H plus. Both of those represent the hydrogen ion concentration. And notice that when there's brackets around it, like I have around these two, that means that we're talking about the concentration being in molarity or moles per liter. So in other words, we're looking at how many hydronium ions are in solution. If there's a lot, then we assume it's acidic. If there's very few, then we assume it is more basic. So the greater the H3O plus concentration increases acidity, and then that would decrease your pH number. Because your pH number, remember, runs from 1 to 14. And the lower number is meaning it's more acidic. A higher number on the pH scale up to 14 is meaning that there is basic. And a pH numbers come from a logarithmic scale looking at the hydronium concentration. So the pOH scale, which probably isn't something that you've heard as much about, looks at the hydroxide ion or OH minus ion concentration in solution. And once again, we're looking at how many hydroxide ions are in solution. So the greater the hydroxide concentration, then that's going to increase how basic something is, which would also increase the pH number. All right, this little relationship right here is very important. We use that a lot. pH plus pOH is equal to 14, and this is a 14.000, indefinite number of zeros, because it's like a constant. So that may become important when we look at sig figs. So remember, your pH scale goes from 0 to 14. If I have anything that's anywhere from 0 to 6.999, then we're going to say it's acidic. pH right at 7 would be neutral. And pH of anything that's 7.01, anything just right over 7 up to 14 is going to be basic. So things like lemon juice are very acidic. You always want to look at the pH. Look at pH to determine if something is acidic or basic. So in other words, these are the numbers we're used to looking at pH. Don't get caught up and look at your pOH. So lemon juice, citric acid, so it's obviously acidic. If its pH is 2, its pOH would be 14 minus 2, so that would give me a pOH of 12.0, one place behind the decimal here, so my answer would have one place behind the decimal. This would be acidic. Here I have a pH of 7, so that's going to be neutral. That's for pure water. So 7.0 would be its pOH. And then milk and magnesia, something that's sometimes used for an upset stomach, has a pH of 10. So it's very basic. If it has a pH of 10, it would have a pOH of 4. 14 minus 10 gives me my 4. All right. So we've talked about water before, and we say that it is amphoteric. Which means that it can act as an acid or it can act as a base. So when we got a bunch of water together, it undergoes something called auto-ionization. So I'll have some water molecules, but this also I will have some of these waters acting as acids and some of the water molecules acting as bases. So I will end up with some hydronium and some hydroxides in there also. So you kind of end up with a mixture of all of those in there. And that concentration, that relationship will change depending upon the temperature. We're not going to spend a lot of time on this. We would have spent more time on this if we were in class. But water does auto-ionize, and we end up with something that's called the ion product constant for water, which is Kw. And Kw is always equal to the hydronium concentration times the hydroxide concentration. And at 25 degrees Celsius, then those two concentration, hydroxide and hydronium, are also always going to be equal to each other. And they'd be 1.0 times 10 to the 7th molar. If we change the temperature, then that would also change. Not going to spend a lot of time on that. You'll see that in AP Chemistry or if you take it in college. But this becomes kind of important. So if we're talking about hydroxide and hydronium concentration, whenever we have something that's a neutral solution, they're going to be equal to each other. If it's acidic, my hydrogen ion concentration should be greater than my hydroxide. And then if it's basic, it should be the other way around, where I have my hydroxide concentration being greater. Now, the calculations that we'll do with our pH, they're really just all going into the calculator, okay? So they're pretty basic. You just have to follow what you're doing with the calculator. So these are going to be our formulas that we're going to be using right here. And they just all go into the calculator. My pH is going to be equal to the negative. That's not the minus log, the negative log of my hydronium concentration. Remember, that could be written this way or it could be written that way. My pOH is a negative log of my hydroxide concentration. And then if I have my pH or my pOH, I can use those to kind of reverse and find those molarities of my hydronium or on my hydroxide. And that's called your anti-log. So if I knew what my pH was, I could take 10, raise it up to my negative pH, and that would give me what my hydronium concentration are. Now we're going to be dealing with strong acids and with strong bases. So remember, a strong acid and base ionize 100%. And we talked about that at the very beginning of our notes. This is also, like I said, going to be an important relationship right here. So kind of a few things you got to do is you got to look at what compound you're starting with, and you have to realize, am I working with the base and I'm going to have hydroxide produced first, or am I working with an acid and I would have hydronium produced? So if I wanted to find the pH, let's say, but I was working with a base, I would have to find the pOH first and subtract it from 14. So sometimes you kind of have to work around in a circle to get what you need. All right, so let's hear. What is the pH of a 0.001 molar sodium hydroxide? So sodium hydroxide is a base because it has my hydroxide and it's strong. So it's going to ionize 100%. So that means if this is 0.001 molar, then this is 0.001 molar, and this is 0.001 molar. We did that earlier whenever we were doing our solutions, and we were talking about that in our concentrations. So my first step in here, I want to find my pH. This is a base, so I have my hydroxide. I cannot find my pH directly. So the first thing I'm going to have to do is find my pOH. pOH is equal to, right here, negative log of my 0.001. And that is what I would put into my calculator. The negative sign, then I would find the log, not the ln, the log log, and put 0.001. And let me get over here to my notes. And when I do that, I get a pOH of 3.0. The question asked what the pH was. So to get my pH, I'm going to take 14 minus 3.0, and I'm going to end up with a pH of 11. So that's what I mean. Sometimes you kind of have to work around it a little bit. So an important thing about, Important thing about sig figs here on our pH scales, because I know how much y'all love sig figs, and they're a little bit different. And it's kind of a pain. So that's what this little italicized statement says. Significant figures in pH. When counting significant figures, only count what comes after the decimal in a pH or a pOH value. For example, the number of sig figs, if my pH is equal to 12.01, that has 2 sig figs. We only count what comes after the decimal. And that's because of the fact that it's a logarithmic scale. If I had pH is equal to 12.0, that would be one significant figure. So if we go back to this problem that we worked, I started with 1 sig fig. 0.001 molar is 1 sig fig. So when I gave my pH, when I gave my final answer that I was asking for, I wanted it to have 1 sig fig. So that's why I said my pH is equal to 11.0. It's the number after the decimal that counts as my sig fig. All right. So trying to show you a little bit on your calculator here, and you're going to have to work with it. But this is the negative right here that you want to be using, not minus. So when I do negative log, I want to be using my negative down here. Okay? And then my log is this log over here, log. Hold on, I see that that's not showing y'all. Let me show you. Okay? So right here, I want to use this as my negative. So if I'm saying that, if I'm trying to find my pH is equal to negative log, and we'll say my concentration was 0.033, then I'm going to go negative log, and then I would type in 0.033, and then I would hit my enter on that one. Let's say that I am using my other formula. So my other formula was the anti-log. So let's say that I am trying to find my hydronium ion concentration, and my formula is 10 to the negative pH. 10 raised up to the negative pH. So let's say our pH was 4.1. So I'm going to say 10 raised up to negative 4.1. So I would put in my 10, and then I would use this little caret top right here that's going to get you up to your exponent. And then once again, you use your negative sign, and then you would use your 4.1. Okay? So you're going to have to kind of practice with some of those and make sure that you're getting them so you can see what you're doing. Make sure you don't have any questions on that part. Okay? And if you do, then you can bring those to the Zoom meeting. All right. So let's try a little bit of practice here. All right. So it says, what is the pH of 3.4 times 10 to the 5th molar hydrochloric acid? And let me see where I can get my answers here. Possibly. All right. So the first thing that I notice is this is an acid. Remember, if it starts with a hydrogen, it's an acid. So I can get the pH directly. I don't have to do it, subtract it from that 14. So my formula is pH is equal to negative log of my hydrogen ion concentration. And once again, hydrochloric acid is strong, so it's going to ionize 100%. So this strength applies to all of these. So my hydrogen ion concentration is going to be 3.4 times 10 to the negative fifth. And that's what would go into my calculator. So I'm going to do negative log of 3.4 times 10. And then I need to do my little caret top to raise my exponent up, negative fifth. And then close my parentheses. And I would get an answer. I get something like 4.4685, and then it keeps on. So how do I need to do sig fig wise? This had 2 sig figs, so my answer should have 2 places behind the decimal. So I would have 4.47 would be my correct pH on that one. All right. On my next one, that's an easy one. What is the pH of a solution if the pOH is 5? So I know that those two added together would be equal to 14. So I'm going to say 14 minus 5 would give me a pH of 9. That would be my pH. My 5 had no places behind the decimal, so when I subtract it from that 14, which is really 14.000, continually, like we've talked about before with constants, then we're going to end up having no places behind the decimal as far as our sig figs go. All right, we're going to skip the next one. And then I'm going to, because it just goes into a little bit more depth. Like I said, we're just kind of hitting what we need to right now, just to give you the basic idea. All right. So the next one says, what is the pOH of a 1.1 times 10 to the negative fifth molar? And that is nitric acid. It starts with a hydrogen, so that's an acid. And then the other thing that I noticed is this is 2 sig figs. Now it wants a pOH. This is an acid, so I have to use this concentration to get the pH first. And then I can subtract that from 14. So I can't go directly to the pOH because that's from a base and this is an acid. So my first thing I'm going to do is going to get my pH is going to be equal to negative log of my hydronium concentration. And once again, this is a strong acid, so that would be 1.1 times 10 to the negative 5. And that's what would go into my calculator. And so from that, I got me a pH of 4.96. 2 places behind the decimal because of my 2 sig figs. But the question is, what is the pOH? So my final step is I'm going to take my 14 minus my 4.96, and I end up getting 9.04, and that is my pOH. 2 places behind the decimal when I subtract it, so I wanted my answer to have 2 places behind the decimal. This 14 is not going to determine it because it's 14.000. All right, and last example that we'll do here is if the pH of a potassium hydroxide solution is 10.75. So a couple of things that I noticed here. I noticed that's a base. I noticed this has 2 sig figs because that's a pH number 2 places behind. What is the molar concentration? Which is what I'm finding whenever I find anything in brackets. That's going to be my molarity. What is the pOH? And what is the hydronium ion? So I'm trying to find pOH, OH minus, and H plus. Those are the 3 things I'm trying to find. So I'm going to do my easy one first. I need my pOH. Well, that's just going to be a subtraction. So I'm going to say 14 minus 10.75 is going to be, because, let's see, that's my pH. 10.75 is going to be 9.04, and that is my pOH. So that is taken care of. Next, I need my hydroxide, my OH concentration. So we would use our pOH for that. And we say our hydroxide concentration is going to be equal to 10 raised up to our negative pOH. That's the formula. So it's going to be hydroxide is going to be 10 to the negative, raised up to the negative 9.04. So let's see if I can find that on here. All right, let's regroup on that one because I could see I was getting answers from a different problem. They didn't make any sense. So obviously my subtraction was wrong there. So I want to get my pH. So I'm going to say 14. Oh, let me get out of my eraser. 14 minus 10.75 is going to be equal to 3.25. That makes a lot more sense. And that is my pOH. Okay, so we still got our pOH. So my next one now, if I want to find my hydroxide concentration, that formula is 10 raised up to my negative pOH. So that's going to be negative 3.25. So that goes into your calculator. 10, and then you would do your little caret top, negative 3.25, and I would get my hydroxide concentration is going to be equal to 5.6 times 10 to the negative 4th molar. So there's my hydroxide. I'm still carrying forth with my 2 sig figs. And then my last thing is I need my hydrogen or hydronium concentration. So that's going to be 10 raised up to the negative pH. So that's going to be 10 to the negative, what was my 10.75. So I'm going to get hydrogen ion concentration of 1.8 times 10 to the negative 11th molar. So that would be then my other one, and that would be my information. Then you ask, was this basic or was this an acidic solution? Remember, always go to your pH. That's what we're used to working with. So this was a basic solution. All right, I think we'll stop right there. And so bring your notes with you to class. We're going to do some other examples that I have pulled up. And after you watch this video, you also will have a Kahoot to take that will have just a few problems in it. And I will see y'all on Wednesday.